Hello and welcome to section 6.8, where we're going to be talking a bit about mechanism more specifically, especially how to do arrow pushing and the patterns that we can expect to see in our mechanisms. There are four fundamental organic chemistry patterns that we should expect to come across here in our studies, and those are nucleophilic attack, loss of a leaving group, proton transfer, and rearrangement. We'll go into each of these in this lecture, but first, let me remind you a little bit about where we've seen arrow pushing already. So previously, we saw arrow pushing in two different sections. We had, in one section, acid-base reactions, right? Where a lone pair on an acid, or on the base, takes a proton from the acid. And that was in some kind of equilibrium. To give us these molecules. So we're going to be using patterns that look very similar to these types of arrow pushing mechanisms. And as you notice, as we did in the acid-base chapter, my arrow started from a lone pair or an area of high electron density, and it ended at an area of low electron density or an electrophile, which is what we learned in the past chapter. So either we could say an acid base or a base takes a proton from the acid here, or a nucleophile attacks an electrophile. And just to reiterate this one more time, whenever you have an arrow you need to make, so let's say we have this nitrogen, this one has a negative charge, very high electron density, makes it a good nucleophile. And let's say you need to attack something. The arrows need to start at the area of high electron density, and they need to end at the area of low electron density. Okay, now let's have a look at our four patterns again. Once again, we have nucleophilic attack, loss of leaving group, proton transfer, and rearrangement. So let's look a little more carefully at the nucleophilic attack one. This is something that we covered a little bit in passing in the last section. But here, the basics are that you have some nucleophile, say this ethanol here, ethanol has lone pair electrons that can also serve as a nucleophile, especially if there's a good electrophile like this acid chloride. Acid chloride groups are not something we've seen before, but what you need to know is that primarily there are two types of dipole interactions here. One from the carbon towards the chloride, because the chloride is more electronegative and is pulling electron density away from the carbon, and one from the carbon up to the oxygen, because the oxygen is also more electronegative and is pulling electron density away from the carbon. Both of these things together mean that that carbon has a very high partial positive charge, and the partial negative charges are on the oxygen and carbon chloride. So this makes that carbon a very good electrophile. All right, so now that we have our region of electron density, which is the alcohol's lone pairs, we can then have an arrow that goes from the lone pair on the oxygen to that electron, electrophile. But once this happens, if you notice, then the carbon, the electrophilic carbon, will have too many electrons. It'll have 10 instead of the 8 that it wants. So just like we did in the resonance, in the resonance section, the electrons from this double bond are going to flow up to the oxygen. And when they do that, our product of this reaction will look like this, where we have now here's that oxygen, and it's hydrogen here, and it attacked the carbon with the oxygen that now has a negative charge, and the chloride. So that's one type of nucleophilic attack we can have. We can also have perhaps just a negative charge of a nucleophile attacking a positive charge. Like this, where maybe you have, let's say, a negatively charged carbon that's coming into contact with a positively charged carbon. So a positively charged carbon isn't a partial positive charge, that's a full positive charge, which is very electrophilic. And because it's so electrophilic, it's very easy now for the lone pairs on that negatively charged carbon, which is a strong electrophile, to then attack, leaving us with this product. Okay, so our next one is called loss of a leaving group. So here, this comes into play when perhaps you have some group like maybe a nitrogen as your nucleophile, and the nitrogen is going to attack, or it comes into close proximity to this molecule, this ethyl bromide here. And like we said before, the bromide has a negative charge, or a partial negative charge, because there's a dipole pulling away the electron density from the carbon that now has a partial positive charge. And because of this partial positive charge, it's a good electrophile for the lone pair on the nitrogen to attack that carbon. And here's where the loss of a leaving group event takes place, because now that carbon would have 5 bonds to it, right? And carbon doesn't want to have 5 bonds. But unlike the above example, where we could just push electrons onto the oxygen, we don't have a resonance structure we can form. So the loss of a leaving group occurs by the bromine kind of taking its electrons and leaving, to give us this product. There's also the bromide ion that's still around because it left from the molecule. Okay, and our third is called proton transfer, and this is something that we covered pretty extensively in chapter 3, actually, but it's something that is still relevant to us here and now because it's still a type of mechanism that is one of the 4 fundamental organic chemistry mechanisms. And in this mechanism, you have, let's say, acetic acid or vinegar here. And this comes into close proximity with, let's say, maybe water. And because the proton is just a nucleus and is relatively electrophilic, and because water's lone pair can be nucleophilic, we start at an area of high electron density, go to low electron density to take the hydrogen or the proton, and the electrons that were on the oxygen just go right back to the oxygen. When that happens, our products here are the acetate ion. There we are. And the hydronium ion. There we are. Okay, so we have one last mechanism to cover, or a fundamental mechanistic step to cover, and that is the rearrangement step. So this is a tough one because it's something that we haven't really ever seen before, and it has basis in relative stability of what are called carpal cations. So if you remember, and if not, we'll have a refresher right here. A carpal cation is what it's called when there's a carbon atom with a positive charge. And strangely enough, the positive charge on a carbon can either be somewhat stable or really not stable at all, depending on what type of carbon that positive charge is sitting on. For instance, CH3 plus, the methyl carbocation, is extremely unstable. But as you add more carbons onto the carbon that has a positive charge, ethyl cation here, it is a lot more stable than the methyl cation, and the 2-propyl cation is more stable than the ethyl cation, and the tertiary butyl cation here is way more stable than all 3 of them combined. And so hopefully you're noticing a pattern that depending on if it's primary, which is what we call something that is on the end here or here of a chain, the methyl is just a 1-carbon chain, or is secondary, which means there are 2 carbon-carbon bonds, or tertiary, which means there are 3 carbon-carbon bonds, that as you increase in number here, you get much, much increased stability. It also depends on if there's resonance available. So for instance, we talked in chapter was that? the chapter on resonance. I think it was chapter 2. Yes. In chapter 2, we talked about the allyl cation, right? I don't want to use that pen. We talked about the allyl cation and how it had resonance that changed where the positive charge could be. Well, typically, this is a primary carbocation, and we just said those are pretty unstable. Well, if you can use a resonance structure to spread out that positive charge, then each carbon feels much less than a normal positive charge, and so the carbocation is much more stable than it normally would be. So that's one way the stability can be increased. Another way is if there is some kind of well, I guess there's really more in resonance, because you can also have something. Oh, I want to do the ink to shape, like we saw in our first homework, or one of our first homeworks, where if you have a conjugated system, a larger conjugated system, and a primary carbocation that can participate in that larger resonance system, then you can also have much increased stability. So the resonance argument makes sense because it's something that we talked about before. But the previous one, the one we were just talking about, where going from primary to secondary to tertiary increases stability, is a little more difficult to grasp, right? Because we haven't really talked about that very much. And it's rooted in this kind of weird phenomenon called hyperpolarization, where just like, maybe not just like, where let's say you have two carbons here. One has a positive charge. If you remember, that positive charge is sitting in a p orbital. But the carbon, if it has a carbon next to it, that carbon is bonded to something using an sp3 orbital, right? So maybe it's a hydrogen over here doing the bonding. But there is some overlap between these two. There isn't perfect overlap, because if you remember, the sp3 orbitals are tetrahedral, and the p orbitals basically sit on the exact, like right above the carbon. But there is some, and it's enough overlap that that little bit of electron density can help stabilize the positive charge. Because even though a full positive charge is very destabilizing for a molecule, it's much less destabilizing if you can have some kind of addition of electron density there. So here, one carbon makes it pretty stable, or at least more stable than without. And if you had two carbons with two different sp3 orbitals, then that's even more stable. And then if you had three carbons with an sp3 orbital, that really stabilizes that partial positive charge, or the what is a full positive charge on the carbon, but turns out to be much less than a full positive because of all that hyperconjugative resonance stabilization there. Okay, so now we're actually getting into what rearrangements are and why they happen. And this is where it's about to get weird. Because let's say you had a molecule like this. And a full positive on this carbon. I'm drawing each carbon very intentionally. That way you can see all the details and don't have to worry about where hydrogens are or positive charges are. There we are. Let's say you have this molecule. This primary carbocation is so unstable, the molecule has a rearrangement of where the carbocation is in order to increase the stability of this molecule. So what ends up happening is that one hydrogen will shift over and move the partial or the full positive charge. So now we have these H's over here. And a positive charge on the middle carbon. And this happens very quickly. The stability increase is so large, basically as soon as it can, like within an extreme fraction of a second, this rearrangement will occur. And in fact, if you tried to make this molecule on the left, you would only find the molecule on the right when you went to look for the molecule on the left. And the rearrangements can happen in a lot of different ways because they will happen if they can. So if you have, let's say, this molecule, where the formula here is C12345, H, well, I guess there's a positive charge here, H 2, 5, 8, 11, the same thing occurs, except this time, instead of a proton moving, it's a carbon that moves. So when this happens, you end up with this molecule. Same molecular formula, C5H11. The only thing that changed is that one of these carbons, this one, moved to the other carbon in order to stabilize that carbocation. These are called on the left, the hydrogen movement is called a hydride shift, and on the right is called a methyl shift. This has been section 6.9. Or 6.8, sorry.